All right, so we got that vector thing out of the way. So a vector is an entity, a mathematical term with direction and magnitude. Oh, I didn't prepare my notes. Or my notes. So if you've taken physics before, you've probably seen vectors, and you may have seen vectors in the pre-calculus class. I think that would be another place where they might have done vectors. I think Professor Hoffman tried to squeeze the idea of vectors in there one day or 2 days. So what we're going to do is we're going to work with vectors, and it's going to be one of our main tools to study stuff in both in 2 dimensions and 3 dimensions, but we can, again, abstractly think about these things in higher dimensions, but for us, we'll stick with the 2 and 3 dimensions. If you're going into linear algebra, the idea of vectors in higher dimensions will be important because it applies in a bunch of different aspects of sciences. Data science, for example, and a bunch of other things. So line segment with direction and magnitude, 2 vectors are equivalent if they have the same direction and magnitude. And the idea behind that is that a vector can be placed in a bunch of different places. So let's see if I can, instead of drawing it, maybe I can just draw a line segment. So if I take that vector and move it around, these 2 are essentially going to be the same vector, even though they're not in the same place. And so what we're interested in doing is resolving a vector and then being able to write a vector. So what I'd like you to think about is a vector is essentially a point. Well, we write a vector as if we write a point. And in the past, I've been kind of loose with the notation, and I would write vectors in open parentheses, but I think I did pretty well last semester when I taught this class where all my vectors are of this form with the, what do you call these brackets? Angle brackets. Angle brackets. So these angle brackets make up your vector notation. At least that's one way to establish the notation. So resolving a vector by placing the tail of the vector at the origin. So let's start off by looking at vectors in 2 dimensions. And we can think about the vector as a line segment. And so a line segment can usually be defined by 2 points, a starting and ending point. So the starting point we usually call the tail, and then the ending point we usually call the head. So based on our head and our tail, we can take a look at a vector. Regardless of where it is, we can send it back to the origin, and then we can therefore what's called resolving a vector. So let's draw a vector in our 2-dimensional plane for now. And let's say its tail starts off at like 1, 1, and its head will go to, let's do 3, let's go to 3, 2. And so the vector that we're actually looking at is a vector whose head is at 3, 2, and whose tail is at 1, 1. Okay. So to resolve this vector, or the term resolving means to try to give a name to this vector. To resolve this vector, what you want to do is you want to take this vector and move it so that its tail is at the origin. Okay, and so once you move it so that its tail is at the origin, you look at where it's pointing, and that looks like another vector. You look at where it's pointing. Where is it pointing? In the same direction, same magnitude, same direction, so it's the same vector. Direction and magnitude. But what's that green point, or what's that point where that vector whose tail is at the origin is pointing to? What's that head? 2, 1. Now, how do we get 2, 1? Subtract. So we're essentially just subtracting. So how did we get this? 3, 2 minus 1, 1. Now, we didn't really formally define this, but when we do that subtraction, we would subtract 3 minus 1 and 2 minus 1. And that's how we get 2, 1. So then I would label this vector, maybe call it V. So a couple of notation that we're going to be using, notational ideas that we're going to be using. To, you know how if we have a number, we just say X or Y or A or B or whatever, or N. If we're talking about a vector, we usually denote it by V, W, something like that. Sometimes, but very rarely, we'll use A, B, C. And there's 2 ways to denote a vector. One is to make it boldface, which is kind of hard to do when you're writing. You know, if you're typing stuff on a computer, it's easy to boldface, but when you're writing, it's kind of hard to boldface. And so instead of boldfacing, the other way to write a vector is with an arrow on top. And an arrow on top would denote that it's a vector. So let's say this is a vector V, and then that vector V will be the vector 2, 1. And we'll dig deeper into that idea of calling it 2, 1, and then having other kinds of notation. Again, if you've had physics, you might have studied I's and J's and IJK. And so we'll talk about what those are and how they fit into this vector. All right, so that's our beginning ideas of vectors. By the way, this vector, whose tail is at the origin, this is a vector. Vector V is in what we call standard position. Okay. Yeah, let me try something here. Not quite. How about just regular text? Ooh, closer. All right. It's even the same color. Okay, so that's a vector, and a vector in standard position. And this is one way to resolve a vector that's not sitting at the origin. At least we can drag it down so that its tail is the origin, standard position, and then wherever it's pointing is the name of the vector. Okay. All right. So now let's take a look at more ideas about vectors. What can we do with vectors? We can add them. Two vectors, u and v. if you position them so that their tails are together, or you can move one tail to the head of the other, then you can define the sum of the two vectors as going from the tail of u to the head of u, and then the tail of v connected to the head of u to the head of v. Well, I don't know, that was pretty confusing. I got confused just saying it. So why don't we just see a picture that would have that information. And so to visualize an addition of vectors, we can put it from tail to head. So u plus v in this case is going to be the vector u, and then you stop at where the head is for vector u, and then you pick it up from there and put the tail of vector v, and then wherever that ends is going to be the new position, the new head of the new vector that we're looking for, which is a sum. We can see that if we take u and v and form a parallelogram out of it, then this diagonal from the tail, where the tails start, turn out to be the diagonal of that parallelogram. Okay. Any questions about this so far? We did subtraction before we defined subtraction up here, and addition would be similar. So if we had two vectors and we were adding it, we would just add the components. So for example, if we have v is equal to a vector like 1, 2, and u is a vector like -3, 5, we can add these two vectors. V plus u is equal to 1 plus -3, comma 2 plus 5. And so that's going to give us a vector -2, comma 7. Okay. And I looked in Desmos. Desmos, they do line segments, but they don't do vectors with arrows and stuff. So too bad. Okay. So any questions so far? All right. So that's the sum of vectors. So what else can we do with it? We can, well, subtract. Is that next? Oh, we can scalar multiply. I don't know why subtraction doesn't come next. Let's do subtraction first. No, let's do scalar multiply first. Sorry, you guys starting to write stuff down. So I just realized why they do scalar multiplication first. It's because subtraction, ooh, there's more room there. It's because to do subtraction, we're going to scalar multiply by -1. So a scalar multiplication, a scalar, we could define a scalar as a real number. So all this time we've been dealing with real numbers as our main number tool that we're doing, that we do stuff with. Anything that we've learned in the past, we can all refer to them as scalars. So a scalar is a real number, and a vector v is a vector. So you can scale. That's where the name comes from. You can scale a vector by multiplying it by a real number. And then that would just either stretch or compress the vector. If your scalar is bigger than 1, it would stretch it. And if your scalar is less than 1, it would compress it. If your scalar is negative, it'll have your vector pointing the other way. Okay. So here are a couple examples. You can 2v, you can 1/2 v it. You can -v it or -1.5v, and then it would be going in opposite directions. So that's the idea behind a scalar. There's also this thing called a zero vector, which is just 0, 0. And essentially it's a point, but sometimes it's good to refer to it as a vector because, well, when we add vectors, our result is a vector, and we subtract vectors, our result is a vector. So even though it's 0, 0, and it doesn't look like it's pointing anywhere, it's just, we would call it a degenerate vector. All right, so that's the idea behind scalar multiplication. So a subtraction would be an addition with a scaled vector by one of the vectors being scaled by -1. So we can think about it that way. That's one way to think about it, but when we see pictures, I think there's going to be an easier and nicer way to think about it that complements the addition of vectors. So subtraction. The difference between the two vectors, it's like adding with a scalar, multiplying. So one way to draw this, this is, maybe I should do it instead of having this drawing. So if I draw it, you can kind of see it happen. So let's say, this is U and this is V. So what we're going to do is we're going to take V and multiply V by -1. So it's going to be the same length, except it's going to be going in the opposite direction as V. And then what we want to do is we want to add U plus -V. U plus -V. So this is U. And -V, if I add it, I would have to take this, maybe I could just pick this up. Copy. I think my original U wasn't very good. Maybe I'll pick this up too and copy it. Come on. So that's U. That's V. So then the result would be from the tail of U to the head of V. So this is going to be U plus -V. Okay. So what's significant about that? Well, it turns out that it's really interesting. It's more interesting than if we look at it from the other perspective. David? Yeah. What is like the V going should be, because the idea is addition is commutative. So if I would do -V plus U, it should get the same thing. All right, but I want to take this vector that we just found. I thought I copied it. Copy, paste, and then put it back to where the original U and V are. And it's not a coincidence, although my drawing might be a little off. But since I copied and pasted things, right, it's the same vector. So it's not a coincidence that this is actually connecting the heads of U and V. So, so we can think about U minus V as connecting the heads of U and V. So when we're connecting the heads of U and V, there's one more thing to consider. Which way is it going? Right? Because an arrow, a connection arrow, you know, we have to distinguish between where's the head and where's the tail. So it turns out that the head is first. And so if you want to identify which is which, the head will be on U, and then the tail will be on V. Okay. All right, if we summarize all this, or at least the addition and subtraction, there's a neat result that happens. And we could draw that parallelogram again, where we would draw these vectors parallel to U and V. And then we saw that when we added them together, we went from the beginning to the other diagonal. So we ended up going on a diagonal. This is U plus V. And then now we just saw that if we subtracted, we get the other diagonal. Well, we didn't see the diagonal because we didn't have a parallelogram, but now that we do, turns out that the other diagonal is the subtraction, is the difference between U and V. Pretty cool, huh? Yeah. All right. Questions? Scale multiplication, addition, subtraction. All right, just running along here. Let's see what else we got. A vector has magnitude and direction. Let's take a look at the magnitude. The magnitude is essentially the length, and we know how to find the lengths in 2 or even 3 dimensions. You remember that thing yesterday that we didn't do in class because we're running out of time? Yeah, it's in your notes. There you go. You're responsible for it now. And so the length is essentially the distance between the head and the tail. And whether you take the head first and the tail, or the tail first and the head, you're finding the distance, so it'll be positive. So the notation that we use for that generally is a double vertical bar. But I want to vouch for this idea that you can also take the absolute value of that, and that would mean the same thing. So having a single bar, like the absolute value that we know of for real numbers, is the same thing as finding the length, because what is the absolute value of the real number? It's just the positive distance to the origin. So that's exactly what the length of the vector is. If you put it in standard position, it'll be the positive distance from the origin. So in 2D, and I'm going to start with 2D, but I'm going to leave space here for 1D. So in 2 dimensions, if you're going from 0, 0 to the point AB, then it's like saying it's going to be A minus 0 squared plus B minus 0 squared. So it's A squared plus B squared under a square root. So as if this is your V, then your magnitude of V is equal to that. If you're in 3D, and your V is ABC, then I'm not going to rewrite it, but the magnitude is just the square root of a squared plus b squared plus c squared. What if the tail is not an origin? Then we go back to the idea that you resolve the vector first. You either send it to the origin or you do the subtraction, and then it'll be the same. Well, if you name a vector ABC, you're going to assume it's in standard position and it's pointing, its tail is in 0, 0, 0, and then its head is in ABC. In fact, in higher dimensions, if you call a vector 7, 4, 3, 2, then you know that that's sitting at the origin pointing at the point, 4-dimensional point 7, 4, 3, 2. We can't see it, but that's the idea. And so I want to go back to 1 dimension. You can think about just from 0, you can just have a point going to A. And you can think about it that as just a vector. This is really just a line segment. And so what's the distance of that? The absolute value of A. And if you follow through, it's like the square root of A squared, A minus 0 squared, which is the square root of A squared, which we know should be positive. Okay. So in math, that's another way to write the absolute value. It's different though, you have to be careful because this is not necessarily equal to the square root of A quantity squared. Although we kind of learned that that's true, we learned that that's true really for only certain values of A, for positive, non-negative values of A, because if A was negative, then under a square root is imaginary. Then you're in a whole lot of complex problems. Get it? Complex. Whatever. Okay. So that's the magnitude. That's how we find the magnitude. So a lot of times I'll do the double bars, but sometimes when I'm trying to write fast, the single bars would mean the same thing. Okay. There's one more unit vector. So a unit vector is a vector of length 1. So what that means is that we're more concerned about the direction and the size doesn't matter. That's what she said. So for those cases, we're interested in just focusing on a vector with direction and then making it into a unit vector because it's the most convenient to deal with. And so what we can do is that if we have a vector that's not a unit vector, we can make it into a unit vector by, quote, normalizing it. And we normalize a vector by dividing it by its magnitude. Okay, so let's take our simple example of 2, 1, if that's our vector. So V is equal to 2, 1. And let's try to see if we can normalize it. So it says we have to divide by its magnitude. So first we have to find its magnitude. So what is its magnitude? So absolute value of V, or magnitude of V, is equal to the square root of 2 squared plus 1 squared, or 5, square root of 5, right? And so we have to divide by, oh, we haven't really defined division. Oh, but it's the same thing as multiplying, right? Yeah. Well, inverse, reciprocal. Don't say flip. Reciprocal. So a unit vector would be, well, we can write this in a couple of different ways, and I'll circle my preference. So my preference would be the second one. It's just the same thing as multiplying by its reciprocal. And if you really, really want to write it in component, you could say 2 root 5, comma 1 root 5. And I encourage you to take the magnitude of this new vector and show that the magnitude is in fact equal to 1. But you know, you shouldn't believe everything I say. Who knows? Maybe I'm just talking all kinds of crap here. None of this is true. I'll let you do that in your philosophy class. Oh, I'm just kidding. Professor hears this. Okay, let's move on. Okay, we have a unit vector. We know what the unit vector is. Well, there's all kinds of other stuff, but let's talk more about the idea of a unit vector. Now, let's say we have a vector. Let's keep using the same vector. And let's say I want a vector going in the same direction, or maybe even opposite. Let's go with the same direction first. So find vector, same direction. Direction as V, but with length 10. All right, so how would you do this? Why don't you guys spend a couple of minutes thinking about it? Maybe I can pause the recording. All right, so 10V, if you thought the answer was 10V, it's a good thought, but it's not correct. Why? Because 10V is equal to 20 comma 10. If you just multiply that by 10, and that's if we take the magnitude of that, this is 20 squared plus 10 squared, which is, oh geez, I don't know. What is it? 500? And if we want it to be length 10, then the answer should have been square root of 100, right? So clearly, this doesn't work. It scales it by a factor of 10. So you have this vector that's not of unit length, and you multiply it by 10, so it's going to get scaled up by 10. But if I want length 10 exactly, then what I would need to do is shrink it to a unit vector, or make it into a unit vector first, and then multiply that by 10. So what you need to do this is to make a unit vector. So make a unit vector, and we found that already, right? And then you take this unit vector and you multiply it by 10. So 10u is going to be 10 over root 5 to 1, which again, you can leave like that, or you can distribute 20 over root 5, comma, 10 over root 5. And so there you have a unit vector going in the same direction as 2, 1, but it has length equal to 10. Okay. Any questions? Okay. What else can we do? Yeah. I don't know if you can square vectors. We'll see what we mean by squaring vectors. Square something, you need to multiply it, right? So we have scalar multiplication right now, but we don't have ways to multiply two vectors together. And we're about to do that soon. Actually. Oh, the 1 over square root of 5 came from the previous page when we're making it into a unit vector. So to make it into a unit vector, it has to have length 1. And we make it into a unit vector by dividing by its magnitude. And so again, I didn't show you, but you should find the magnitude of this vector here, the vector u, and show yourself that it actually has unit length. Okay. Any questions? So these vectors are going to be our tools to doing stuff. That's all I have in my notes. I have a feeling there's more. Yeah, that's in the next section already. Well, let's go into the dot product. What? Or we can do outplot 3D. Yeah. So it takes vectors, but it takes vectors in 3D. I mean, you could take a look at vectors in 2 dimensions if you want. All right, so this is our vector, 1, 1, or negative 1, comma 1, comma 1. Maybe you guys can help me make vectors that would draw a box around this. You know how if we have a point in 3-dimensional space, you can kind of define a cube. It goes along the X, along the Y, and along the Z. So let's fill this up with some vectors. I should have you do this. What? A vector box. Is that what it's called? All right, here, let me start what I mean by this. Yeah, 0, 1, 0. All right, so I have 3 vectors coming from the origin. Yeah, so I did all my examples that because they all come from the origin. Let me do one that doesn't come from the origin. All right, here's what I want. I want a vector from this point, from so I want a vector 0. So I'm going to have it go from the z-axis, and then I want it to be parallel to the xy plane going along the y-axis. So 0, 1, 0 or 0, 1, 1? No, I don't want it to touch the y-axis. 0, 1, 0. You see that? Maybe I should give this to you as an assignment. All right, so let me think about this. Let's go to the next section. So when approaching the dot product, people usually come from it from two different ways, two different perspectives. We will, I guess for today, we'll just focus on defining the dot product. And the dot product will be defined algebraically and geometrically. Algebraically is, let's call it computationally. And this is going to be our way to compute the dot product. So if you have a couple of vectors and this dot product idea works for 2 dimensions, 3 dimensions, and higher dimensions. If you have 2 vectors, then the dot product is going to be defined by, first, the notation is going to be, well, a dot in the middle. And then the result is going to be the first components multiplied together plus the second components multiplied together plus the third components multiplied together. Now, you have to tell me one thing that comes out of this. What should be the first thing that you would notice about this dot product? It's no longer a vector. It's a scalar, right? So that's going to be an important aspect for checking yourselves with rules and properties later on, that the dot product gives you a scalar. So this is sometimes called a scalar product just because of that fact that you get a scalar. And so the dot product gives you a scalar. And here's a simple example. A dot would be if A was equal to, what is it? Oh, I didn't talk about the IJK. Ooh, maybe. Yeah, maybe that's what I forgot. Sorry. Are you guys all taking notes like in order and stuff? Too bad. I'm sorry. sorry, my bad. Let's talk about IJK. So there's no distinction between 2-dimensional and 3-dimensional IJ, but if there's a K involved, you know it's going to be 3D. So the IJ in 2 dimensions and the IJK in 3 dimensions are called the standard basis vectors. And they're called the standard basis vectors because you can write any vector as what they call a linear combination of these vectors. So let's just 3D here. And let's take, for example, let me take a peek at the dot product example. 4, 3, 0, 4, 0, 4, negative 3. So let's say your vector is 0, 4, negative 3. If you're in standard position, which means your tail is at the origin, then you can go from there to the point as if it was a point 0, 4, negative 3. And how would you get to that point? You would move 0 in the x direction. You would move 4 in the y direction, and then you would move by negative 3 in the j direction. Hey, sorry. You would move z. Okay. So what that means is that we can write this as 0 times 0, 0, 1. Oh, messing up here. Let's try that again. 0 times 1, 0, 0 plus 4 times 0, 1, 0 plus negative 3 times 0, 0, 1. And 1, 0, 0 is I, 0, 1, 0 is j, and 0, 0, 1 is k. Okay, yeah. They're scalars that scale the IJK. Okay. Yeah. They're scalars that scale the IJK to get you to the point that you want to be to make your vector. So in physics, they do the IJK a lot. And in this class, we'll use both. If I had a choice, I'd prefer the, what is it again? Angle bracket notation. Okay. So that's the story behind the IJK. And then if you have taken linear algebra or planning to take linear algebra, the whole idea about basis vectors will become a lot more important. Actually, we'll touch on it a little bit more when we study a frame, Frenet frame. We'll get there. All right, now that we've gone over that idea, let's do the dot product real quick. In this example, you have A and B. And so you can stick with the IJK notation, or you can rewrite it as 0, 4, negative 3 for A, and then B is equal to 2, 4, 6. So the dot product A dotted with B is equal to 0 times 2 plus 4 times 4 plus negative 3 times 6. And that would result in a scalar. I think this is, what is it, 16 minus 18, -2. So it's a number. Okay. What is that number? What's it good for? Well, aside from just the computation of the dot product, it might be good to take a look at the dot product from a geometric point of view. And so you can define, and again, some books go from one and then prove the other, and it works out the same way. So I don't want to, not like we're proving anything in this class. So let's just say this is an alternate definition, like alternate facts, an alternate definition of the dot product. So the dot product geometrically can be seen as an angle between two vectors, A and B. Now, in 2 dimensions, that's pretty clear to see. In 3 dimensions, you can kind of visualize it also. If you have 2 vectors, it's the angle between them. So we will just represent this by a 2-dimensional drawing, but we can extend this to 3 dimensions as well. So A dot B would be equal to the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between them. So that's the basic idea behind this. And what this does is that it helps us find angles between vectors, which might be useful. And if I were to find this angle, I can simply solve for cosine theta or go all the way to solve for theta. But if we write cosine theta, this is just the dot product divided by the magnitude of A times the magnitude of B. Cosine. Let's talk about the cosine briefly. What are some of the things about the cosine? When is a cosine positive and when is it negative? Quadrant 1 and 4. So from 0, pi over 2, to pi, right? So from 0 to pi over 2, it's positive. So if your angle is an acute angle, it's positive. From pi over 2 to pi, it's negative. And if you go past pi, it'll be negative and positive. But if you imagine your angle between 2 vectors, if you go past pi, then that means there's another angle on the other side that's representing the same thing. One more important thing, A dot B is equal to what? Dot product is equal to 0 if the 2 vectors are perpendicular. That's going to be a big theorem for us. It's not really a theorem, just a fact. It's going to be a big fact for us. Yeah. Yeah, we'll do that next section. Yeah. All right. So that's it for now. I'll devise some vector activity for you sometime.